I'm Scott Parent. I'm the CTO of our digital solutions business inside of Baker Hughes, headquartered in Houston, Texas. Baker Hughes is an energy technology company operating in 120 countries around the world. We operate in upstream through production, midstream through compression, and downstream through refinery. We monitor gas turbines. We send and sensor both products in the oil and gas and energy space, but also in the aviation and automotive space. We have technologies like industrial CT scanning used to look at parts both for aerospace and space to measure and monitor the quality of those parts that go into service. We have technologies that sit and monitor 30% of the world's wind turbines. And as a company, we spend an awful lot of time subsea, subsurface. We're also a company that provides power and gas turbines used in the oil and gas space, offshore and on land. A very broad technology suite, which is why the challenge of the energy transition is so close to home. Baker, with its portfolio, works very closely with the customers to see what the future will look like, both from a standpoint of fuels, like hydrogen, to infrastructure, like CO2 capture, and new ways of using energy, like geothermal. All these technologies will be needed to meet the Paris Accord zero emission standards. Most of those technologies, unfortunately, are immature. Only about 25% of the technologies we believe we need to get us there are today available on the market, meaning we must evolve and mature the remaining 70% of those technologies faster, more confidently, and to do it more quickly. One way to do that is through simulation. In fact, today, most of the simulation we do in our business supports the products, the mature products that we have today, and will need to be applied, those same methodologies, to those new technologies. At Baker Hughes, we're working on a number of technologies that will help both in mitigating and measuring carbon emissions. We're working on combustion of hydrogen in our gas turbines. We're pushing on emissions management, the measurement of methane and methane plumes. We're spending a lot of time looking at different ways molecularly to capture CO2, both directly from the air and from large point sources. All of these technologies will require a maturity period. Most of the technologies I just described are also today being heavily analyzed using the ANSYS suite of tools. If we think about the way we've developed technology in the last 50 to 100 years, most of it has been through experimentation. Test and tweak, I like to call it. Build and break. And while that is a necessary evolution in the way that we mature our technologies and products, it's not the fastest way. What I've found in this transition is that we have much less time to prove many, many more technologies, and we're going to need all of them. So simulation and the acceleration of the maturity of these products through simulation is going to be an absolute paramount. This is important because it will help us meet the speed in which our customers and our industry needs our help. You know, I'm reminded of a story. When I was at the Research Center for General Electric, I was responsible for all of the design and development tools for the engineers at aviation and power. We had 350 plus PhDs globally working with ANSYS and a few other companies on the latest and greatest analysis tools for things like computational fluid dynamics, vibration, cracking, lifing, heat transfer, aeromechanics. And every quarter, one of the CEOs from one of the businesses would come visit us. One day, Dave Calhoun, who now is the CEO of Boeing, came to visit, and at the time, he was running GE Aviation. And he brought with him a cadre of technical leaders, and Rick Stanley, a friend of mine, the engineering leader. We sat down and we talked about all the programs at the Research Center. And in that conversation, we were discussing a lot of other technologies.
And Dave was very clear
that it was a leap of certainty with these tools that his engineers every year could return to the business higher productive engines, lower noise in some cases, more reliable in every case, better fuel consumption for those engines, lighter weight engines, optimized clearances, and of course, better cost positions. And that these tools and the folks that created these tools for the designers in the business at the Research Center were a critical part of his success plan. There were a lot of discussion at the center, always was, and there was an awful lot of experimental work that would go on, and that was important too. But he recognized that without such tools, we couldn't be the best we could be, and our products couldn't be what they needed to be. Ultimately, the lesson in leadership there was not just that we need to invest in simulation, but we need to look at the generation of leaders in our organization today and suggest to ourselves, are they adapt to working in this new world, this digital world, this world of simulation? Are we still doing the kind of testing we need to do, or are we doing too much testing based upon a leadership that was grown up with a different set of tools? Have we challenged ourselves at the leadership level in engineering and science to listen to some of those new engineers and new scientists that come into our organization who are much more comfortable in simulation, the world of simulation? Are we optimizing the use of simulation to reduce the amount of testing in our organization? He was establishing in the room that not only was testing and tweaking important, but that we had to first be first in understanding the physics and the solutions that would work for our engines. Made it clear that in his quote, "So go the tools, so go the people," was really a lesson in leadership. And that lesson is simply that culturally, if we do not push advanced capabilities and advanced tool sets, then our organizations will continue to do things as we've always done them. The sharper, better tool needs to be brought to bear every time we sit down at the design table. That was Dave's philosophy. That's been my philosophy for the last 20 years since. If we can't allow our engineers to change the methods in which they work using today's best tools, then we are holding our organizations back from a speed and a pace in which this market demands, in which these challenges demand. I challenge my leaders in my organization every day. Do we have enough computational work going on alongside the build and break? Do we have enough engineers focused on the computational side of tweak and test? And if we don't, how do we ensure that leaders like from my generation don't become a barrier to that pace and that learning for younger engineers in our organization? At Baker Hughes, we have a new entrance program for young engineers. We call it Aspire. Engineers come in, and for the first 2 years, they rotate around the business. And one of the first things I say to those folks as I sponsor that program for the company in the technology track is you need to continue to push on those things that do not seem right or contemporary. You know, many of us graduated generations ago and have been working in this industry for a long time. That's okay. We need that leadership too. But what we have to do is be open to the diversity of younger thought, new thought, better ways of doing things, not shy to digital, as many of my generation have been. And they need to be confident enough when they get into the organization to recognize that that diversity of thought, that diversity of application in space is incredibly important if we're going to be the best at what we do. We cannot be stagnant, and our organizations cannot become numb in the mundane of doing things the way we've done them forever. I push those young engineers in our organization to speak up, speak often, and help us in this challenge of the energy transition, because we're all going to need it. At Baker Hughes, we talk a lot about how do we move energy forward, and how are we going to take what we can do with our customers, make the world a better place. The environmental challenge in front of us is well within reach based upon the technologies we've identified to get there. Do we understand what the mix will be? More of this, less renewable, more renewable, less gas, more nuclear? Probably not. That'll evolve over the next decades. The simulation is now new and will be part of our set of tools going forward as scientists and engineers developing and challenged by some of the world's biggest problems. But it is for sure that this generation of engineers, this generation of talent, will be challenged by this for the decades to come.
So how can we affect another person?